Alright, so I want to make a quick video talking about the derivative of a graph telling you the slope at a point on the graph. So we ultimately want to be able to answer questions like this where we have some given graph and we want to be able to sketch the derivative. And in order to do this, let's actually detour over to Desmos for a moment. So in here, my given graph is this purple thing. And to sketch the derivative, it's this piecewise step function that's in green. And how do I know it's the derivative? Well, the derivative should tell you the slope. And this makes sense in the lens of algebra when we're just dealing with lines. So the slope of this line here, well, I could sit and compute it, but I actually wrote some code to tell me. Where is it? Ah, here we go. Let's give me a label. Perfect. So the y value right here, so negative 2.66666 and on and on, so negative 2 2/3, that's telling us where this line is sitting, but that's also telling us the slope of this first purple line segment. And then the second y value, so 0, that's telling us the slope of the second line segment. And the third y value, 2 2/3, is telling us the slope of this last purple line segment. Okay? So the y position of the green graph is telling you the slope of the purple graph. Let me say that again. The y position of the green graph is telling you the slope of the purple graph for the corresponding x values, right? Every x value in this region here has the same slope. It's negative 2 2/3. Every x value in this region here has the same slope. It's 0, and so on and so on. So let's go ahead and get more regions, which I'm going to actually want to slow down this animation. Oh, no, never mind. Point one is fine. We can go a little bit faster, actually. Okay, so 4, 5. Okay, so this works. Let's speed up the animation a little bit. One more, maybe. That works. Okay, so hopefully you see how this is working, right? So all the x values in this region here, which are between x equals negative 2 and x equals negative 1.2, so all of those x values have a slope of negative 3.2. That's what is the slope of this first purple line segment here. I can tell that by just reading off the y value for the green graph. Y values on the green graph tell me slopes on the purple graph. Y values on the green graph tell me slopes on the purple graph. Okay, and if I just kind of let this play through, then that purple graph, even though it's just a bunch of little line segments, by the time we get to 10, it's already looking smoother and smoother and smoother. But the green graph is not looking very smooth, right? There's still a bunch of very obvious big steps happening there. And let me, I think this is the label that I wanted. There we go. That's a little bit more user-friendly. Let's take this off. Okay, great. So, right, the negative 3.6, that's the y value of this green part here, and it's telling us the slope of this first purple segment. And now if I were to zoom in on this purple graph, somewhere where there's a little bit of, you can see a little bit of a kink, right? A little bit of a change in slope. It's kind of steeper here, and then it's less steep here, okay? So let's go ahead and zoom back out. And those kinks correspond to the discrete jumps, where like I go from negative 2.8 to negative 2, for example, or from negative 2 to negative 1.2. And since the green graph is telling us slopes, it can pick up on these kinks a lot easier than our eyeballs can, because, transitioning from like negative 2.8 to negative 2, our eyeballs are not that great at the sensitivity of telling the difference in slope. You can kind of see, like here's a kink here and here's a kink here, but in fact, very quickly, our eyes are just not good enough. So let's go ahead and just make this 20. And now the purple graph is looking pretty smooth, but you can see it's just a bunch of little lines of slightly different slope, right? In the green graph, which is telling us the slopes of all these little lines, makes that a lot clearer. And this green graph is a graph of the derivative of the purple graph. So the green graph, its y values tell you the slope of the purple graph. And that's what a derivative will do. Its y values will tell you the slope of the original function for corresponding x values. So let's go ahead and get rid of these, I don't know, all that business there. And instead, let's just put up the original function. So there's the original function that the purple one was getting closer and closer to. And we can just have Desmos graph the derivative for us. Okay, so f prime is the line y equals 2x. And you can see that because it goes through 0, 0, and it goes through, for example, 2, 4. Okay. And the orange graph, y equals x squared, is the original function. And so apparently, y equals 2x. Here, I'll just, instead of saying f prime, I'll just say y equals 2x. Okay. So the y value is going to tell me the slope of the orange graph at the corresponding x value. So for example, when x equals 0, so here I am, x equals 0. If I do 2 times 0, I still get 0. So my blue function, my y equals 2x, that's saying I have a slope of 0, 0. But if I go to, here, let's highlight some points. So let's say I'm at -1 f of -1. Okay, there I am. And I'm curious, what's its slope? So f prime at -1 is -2. Okay, which again, the line y equals 2x. So if I plug in -1 for x, the output is -2 in the derivative function, right? This is f prime. And that's saying the slope at that green dot there is -2, which, well, it falls right in between where I had a reading of the -2.2 and the -1.8. Those are remnants of back when I had the step function. But this is what a derivative does. It just tells you slope. So if you can just kind of eyeball what a slope is, you can start to draw a derivative graph. As an aside, this little thing I made, if you all want to play with it, I can post the link. How do I, all right, so if I take this away, then we can start to play with that. And if I put up, where is it? Is it you? Yeah, it's you. Then we get those little stairs. And you can actually start to see how slopes behave for whatever function you put here. So if I say sine x, then, oh, that's really gross. Let's get rid of these labels. Great. And so now you can see, so I have a little portion of sine x and how all the little slopes behave. So when I'm passing through x equals 0, that's when I have the steepest slope, and it looks like it's about 1. But when I'm near these peaks, my slope is near 0. In fact, when I'm right at the peak, I should have a slope of 0, but where I'm sampling this curve kind of messes that up. And I also made it where you can go ahead and extend these curves if you want. So anyway, if you all would like this, I can, or maybe I'll just post the Desmos link in the comments and you can play with it if you like. Let's look at another, so in fact, let's make a few comments, right? So notice this purple graph, which is sampling sine x, its slopes also look to be really periodic. So maybe the derivative of sine is some other periodic function. If we play with some polynomials, so maybe I could do like x times x minus 1 times x minus 2. Okay. Well, at certain levels, it's really hard to tell what the result is going to be. So if I just hit play and I just sample more and more, oh, let me get this back to being closer. So we'll do a b value of 3 and an a value of like -1. Okay, there we go. Now it's a little bit easier. So you can see, so the purple graph, the purple graph is a degree 3 polynomial is what's called. If I multiply this all out, multiply out all of f of x, it's going to begin with x cubed. Okay? And there will be other terms, but it'll begin with x cubed. And its derivative looks like an x squared graph, right? This should really go from 1 to, let's just go to 100. Let's be ambitious. Let's go ahead and play. And now we'll start to see these green slope samples are going to approach more and more and more like an x squared, right? And notice again, when the purple graph is near a peak, the green graph is near 0. So I'm looking at the same x values, and that's because the green graph is telling me slopes. When the purple graph is going uphill, the y values on the green graph are positive. when the purple graph is going downhill, the y values on the green graph are negative. And again, that's because y values tell you slope. Slope should be negative when you're going downhill. Okay, so anyway, if you want to play with that, I'll go ahead and post it in the comments. Let's go ahead and sketch the derivative. Let's answer this. And it's a little bit misleading because we're going to have to add to these graphs. I pulled this from the textbook, I think in the back of section like 2.2 or 2.4, I don't remember. Okay, so we have an original function drawn here in blue, and I want to sketch this derivative. So what are some things I should look for? I should look for slope equals 0. Okay, so like here looks like a point where slope is 0, here looks like a point where slope is 0, and maybe even where I begin is a spot where slope is 0. And I'm going to graph the derivative in red. So those black dots I put down, those are not going to be spots on the derivative. They're helping me identify x values. So let me make that more obvious by just making dashed lines telling me these x values. And you know, this one already lies there, so I don't have to dash it. And there we go. All right. So at those x values, the slope looks like it's 0. So the y value that I put down is going to have 0 at those x values because in red, I'm graphing the slope at x. Okay. All right, so now that I've looked for where slope is 0, now I want to look for where my slope is steepest. All right, so let's see. So in black, maybe I'm steepest around here, maybe I'm steepest around here, maybe I'm steepest around here. Okay, does that seem about right? That seems about right. So again, I care about the x value, so let's go ahead and divvy this up. Okay. Great. And I actually need to continue down because we're going to need some negative y values. All right. So right here, my slope is negative going downhill, and it's pretty steep. Maybe that's like -2. So I'm going to put a dot down here. So this dot, whatever its x value is, right? Maybe x is roughly 1.75, but I don't really care. Whatever its x value is, the y value, okay, so this is x, the y value is supposed to be the slope of the blue curve. So I'm supposed to approximate this slope, which I would say is about -2, and that's the y value that I choose. And that's the same rule applies. So here I'm approximating the slope. It's 0, and that's the y value I choose. 0, y value I choose. 0, y value I choose. Okay. So at this first point, it's not as steep as this guy. So maybe this is more like a +1, we'll say. So let's see. Maybe that's around, in fact, there we go. And finally, here's the other steepest point. Maybe this is like a +2. So we'll put you up here. All right, great. And now, if I look at my blue curve, the way I go from 0 up to this steepest point and back down to 0 looks like a pretty smooth transition. So I want to smoothly go from this slope to that slope to this slope. So let's go ahead and just fill it in. Okay, boom. Boom, and same thing, I can kind of just smoothly go here, and oh gosh, this is so hard. Okay, something like that. So this would be a valid derivative approximation, which is really all we're going for here. And you can think of it as a slope graph. So again, whatever point I'm at on my blue curve, I look at its x value, and I think, what is its slope? I don't know, maybe it's like a -1 or something. And that -1 is going to be the corresponding y value for my slope graph. Okay? All right, let's do something more interesting, and then we'll wrap it up and call it good. So, same idea. Let's follow that same algorithm. First thing I do is look for where the slope is 0. Okay, well, peaks and valleys. All right. And then we have this weird point here. And I was talking with a student today who said, well, it looks like the slope is 0. But there's something kind of really different about that point, which, so if we compare these two peaks, there's this idea that if I kind of zoom in enough, there really is more than just a single point at the top here. You know, like this curved graph at the end of the day is still kind of curved. Whereas this graph, we have a very abrupt change. Okay, it's very sudden versus being smooth. And so if you think about what's going on, if I kind of say, okay, well, what's the slope like of this blue curve? Well, it's a positive slope, okay? And it's a big positive number. And it's still big, but it's getting smaller and smaller, okay? As if I was climbing this mountain, then it's easier to climb right here because it's less steep compared to right here, right? And then I can stand on the mountain. And in fact, okay, I'm getting a little tongue-tied with what I'm trying to say. But essentially, all right, I want to give the idea that the slope is smoothly going from something positive to something negative. Whereas here, I have a constant positive slope. Can we approximate it? Yeah, this looks like it's roughly a +1 slope, and this looks like roughly a -1 slope, and it just jumps. There's not a smooth transition. We just kind of hit this corner. And in fact, that's what this is called. It's called a corner. So we want to show that in our slope graph. So let's add that on things to look for. So slope is 0 or undefined or jumps. Okay? And this idea of slope being 0 or undefined, which is a slope jump. So let me just actually get this, or undefined. That's something called a critical point. Critical point. And they're kind of a big deal. And so it sort of makes sense that they're one of the first things our algorithm looks for. So let's go back here. So we identify the critical points. That's the spots where the slopes are 0 or undefined, because it kind of behaves different from the right to the left. Okay, but also we do care about genuine jumps. So these are some things we're going to care about. Okay, so these are all the x values that I care about. So let me go ahead and mark off all these x values. There we go. There we go. There we go. And that was probably supposed to be a 2, and this other jump was supposed to be at 1, most likely. All right. And now, this graph is much busier than the last one, but I can still begin by saying, okay, here's where I'm going to have a slope of 0. So for this x value, my slope is 0, and that's why I put the red dot at y = 0. So the y values of the red dots tell me the slopes of the black dots. Y values of the red dots tell me slopes of the black dots. Okay, but now I don't get to put a 0 dot here because it's actually not defined. Something I can do, though, so we previously talked about how right here the slope looked like it was +1. So I can put a horizontal line at y = 1. Because what I'm saying is, for all the different x values here, they all have the same slope, and it's 1. Okay, but then there's a jump. And I jump down to y = -1. All right, so I really should have continued this xy plane, right, this graph. Okay, and that pretty much takes care of this whole region. I can't put a dot, a closed dot, anywhere on these x values because it's not so clear how to define the slope at this point, right? You might be tempted to say it's 0, and I'm sure there's branches of mathematics that define it as such because it's sort of the average of these two things. But it's really undefined. I don't know how to define the slope right here. So I just have my open dots there. Similarly, I can't define the slope at this x value. It looks different. If I look at it as I come down from the right, it looks like my slope should be +1. because this whole line has slope +1. But if I come up from the left, this kind of looks steeper than this line. So maybe coming up from the left, I was actually a little bit steeper, and I got there from 0. Boom. All right. Or maybe it looks less steep. I don't know. Yeah, I guess it's a little bit steeper. All right. So let's go back to our algorithm on things that we should look at. It's not really an algorithm, but all right, where's the slope steepest? So, all right, it looks like I'm probably steepest right around here, and there's some symmetry, so there. And okay, so since these are the steepest, I'm going to use them as markers for sort of like the furthest that my slope graph goes up and down. So here's my steepest negative, and maybe it's -2. And if this line here was at, or line segment was at y equals -1, then -2 would be like way down here. All right. So I have to go from like 0 down to -2, back up to 1. All right, now I'm starting to fill in a potential slope graph for this blue curve. And now I have my most positive slope, and by symmetry, it looks like it's around a +2. And so I have to, oh man, this is hard. Just not a lot of space to work with. There we go. And in this region here, my graph is decreasing. It's going downhill, so it has a negative slope. And it'll be something like this, or maybe whatever like this, where I am most negative, where my y value is most negative, is where my slope is steepest in the negative direction. Right? Okay, so this is a valid slope graph for this blue graph. All right, just notice my slope graph is in the negatives whenever my blue graph is going downhill. And that's what these dividing lines help me do. They help me figure out where is my slope graph in the negative, where is it in the positive. In other words, where am I decreasing and where am I increasing. So if I look at the blue curve, I'm increasing here. And that's the region where the red graph is in the positive y's. I'm increasing here, and again, red graph, positive y's. I'm decreasing here, red graph, negative y's. Okay, so this doesn't talk at all about the rigorous definition of the derivative, but it gives us some intuition on derivative behavior. One more little remark, which is that derivatives, okay, so here's some shorthand notation. For polynomials, well, they're still polynomials of one less degree. Okay, if your class hasn't gotten here yet, you'll get there soon enough. It's something called a power rule. And this is sort of a fun thing to think about with just the intuition we've talked about so far. So what does a polynomial look like when you graph it? It looks something like this. Okay? In this case, the polynomial that I chose to draw is probably a 1, 2, 3, 4, 5th degree polynomial. So this black curve is probably something of the form some number x to the 5th plus some other number x to the 4th plus some other number x to the 3rd plus it just kind of keeps on going until you run out and you just get okay, let's see, I don't know, pick another number, doesn't matter, some other number x and some other number, right? So it just kind of looks like that. This largest power is called the degree of a polynomial, and in most nice cases, you just count the number of roots that there are, okay? So if I was to graph the derivative of this polynomial, so here's f of x, if I was to graph its derivative, f prime, what would that look like? Well, I should first find where the slope is 0. Okay, so at that x value it's 0, maybe at that x value it's 0, and at that x value it's 0, and at that x value it's 0. And then, because this black curve is just really smooth, continuous, it's very nice, I'm going to use these to kind of break up the sketch of the derivative. And just kind of tell myself, like, okay, well, in this region of x values, my black curve is increasing, right? It's going uphill, so I'm increasing. And what that means is that my slope function, this red curve that I draw, has to have positive y values. So this is my shorthand notation for that. And it looks like it's something kind of like this. I have the biggest positive y value when my slope is steepest. And when my slope is less steep, I have a smaller positive y value. Okay? All right. And if you remember the algorithm, some of the other stuff I should look for are points where I'm steepest. I would say I'm kind of steepest right here. So that's a big negative, so I should just pick some big negative y value. And I kind of want to, oh, you know what? Probably should have just shot for maybe here, and then I can connect it nice and smooth, and boom. Okay, so let me go ahead and erase this. And similarly, maybe around here is where I have the next steepest point. So that's steep in a positive direction, so maybe it's something like this. And so I come up and I touch it and I go back down here. And then maybe somewhere around, oh, I guess I just happen to draw it where the roots are roughly the steepest points. So that's maybe somewhere around here. I put down my steep dot and I have to touch it and come back up to 0. And then I just kind of go up again. Okay, so the black curve was a degree 5 polynomial, and we know that by counting the roots. Okay, which there's a subtle lie there, but don't worry about it. My red curve, what's its degree? Well, 1, 2, 3, 4. Right, so f prime is something like a x to the 4th plus other stuff, when the original function was a x to the 5th plus other stuff. And there could be some number here, so I'll put down a. Okay. Why is that? What happened? Anyway, think about it. See if you can figure out why that occurred. And as a hint, look at peaks rather than roots. Okay, see you next time.